Okay, so I assigned a homework problem that requires design, and I don't think I did any examples that have design in it. So I've selected this problem to help guide you through the process of doing a design for fatigue and for a specific life. So right here, this is problem 619 from the textbook. I think it's the same problem in both the 10th and the 11th edition of Shigley. And so we have these bearings or this shaft. It's rotating, but for some reason the force remains constant right here of 8,000 pounds. And it's rotating at 950 RPM, and it supports this 8,000 pound load. And we're going to use 1095 hot rolled steel. And our goal is to specify a diameter using a design factor of 1.6 for a life of 10 hours, right? So actually, I want to pause just a second to see if perhaps you want to design it so it will fail after 10 hours instead. So just 1 second. Yeah, I might want to try to do it without the safety factor, right? Because I think in the homework assignment, I did not give you a design factor. I just was trying to like let's see what it would take, what this design would be like to fail after 10 hours, right? So that's what we're going to try to do. So we're modifying the problem a little bit. And so we're going to try to make a design diameter. Now they've given us some parameters as guidelines. For your assignment, you could use these. You could use maybe these parameters just as a place to start to get because we need to know a little bit about the relative dimensions from the large to the small diameter, and then also for the fillet radius. So these seem like pretty reasonable things to try to do. So let's set this up and see what we can do. All right, so first you can see the dimensions, and let's just proceed with that. And I need to, no, I think I need to write up a few other things down as we go along, but let's start. All right, so the first thing I want to do is figure out the loads that are on this, and that's not, your homework problem doesn't have that in here. But we do want to try to figure out what our reaction loads are. So we take the sum of the moments, and I guess I'll call this A. Let's call that point B, C, and let's call that D, right? Just to give it some names. And so we'll take the sum of the moments about A and set it equal to 0. And so we only have one load. This is going to be pretty easy. So it's going to be clockwise of 8,000. So clockwise 8,000, and that's going to be times 15 inches. And then here we're going to counterclockwise, so it's positive. So there are 2, and that's going to be 20 inches. So we should be able to do that pretty easy. 8,000, 15, and then divide by 20. Boom. So we get 6,000. R2 is equal to 6,000. We could do the rest in our head, probably, but let's go ahead and do it anyway. Sum of the forces in the y direction equals 0. Up is positive. So we say R1 minus 8,000, and then plus 6,000 equals 0. So we have R1 is equal to 2,000, right? I could do that in my head. And then let's do a shear moment diagram. So the R1 is only 2,000. Right? It's going to drop down 8,000, so this is going to be like 6,000. And not to scale. So you get 2,000, 6,000. And so here's your V, and this is going to be in pounds. I'm going to rewrite my moment line. Move it down some. And these are going to be in inch pounds. And so let's take this over here. So we had 15 times 2,000. I should be able to do that in my head, but I don't trust myself. I think it's going to be 30,000. Yes, it's going to be 30,000. And bing or boom right there. So 30,000. This would be 30,000, not 3,000. 30,000. But we're trying to decide this diameter, right? Here's the goal of this thing is to right here. So it's going to be right here where there's going to be a lot of stress. So we need to find that right there. That's actually the important part. So it's going to be 2,000 times 10 or 20,000 inch-pounds. And I, once again, that is 3,000. Why was I doing that? I don't know. All right, so that's how the loads portion of the thing is. We're going to have that, but that's going to be a repeating load, right? That moment's going to create a bending that's going to go from tension to compression, tension to compression. And our goal now is to find that diameter. But there's a couple of things that we would need to know about the diameter in order to get it. For one is the stress concentration. But we do have the ratios, so that'll help us. But we don't know the specific notch radius, although we do know from the problem that they tell us to make this one is going to be d divided by 10 for the notch radius. And right here they know there's 1.4. So we might be able to look up that K, the KT first, right? So let's get that KT. And we know that we're going to need... let me look it up first. Look up the graph, and there's a fillet in here, so that's going to be this type, and we're going to be bending, so it's going to be this one down here. We need big D over little d. Well, we were told that's going to be, we're recommended to be 1.4, right? And we're going to need 1/10, right? So that's going to be, if we look onto this and we see there's 1.5 and one here, and then there's 0.2. So we're really going to have a KT that's somewhere in the range of like, looks like 1.6 to me, right? So here's 110, and maybe call it, because we're going to be close to 1.5. So here's 1.6. I'm going to say it's 1.65. 1.65. But we want to have the fatigue stress concentration. So we need the notch sensitivity. And in order to get the notch sensitivity, we really need to have the fillet radius, but we don't know the fillet radius right here, right? We need the notch radius, the fillet radius under here, in order to get this, right? Probably in inches is what we need it in. But let's go back to the material then for a moment, right? So the material that we said that we were going to have, let's go back and open this back up. We said we're going to have 1095 hot rolled steel. And so let's look him up. 1095 hot rolled steel. Okay, so we have 1095 hot rolled, and so we're gonna have a tensile strength or ultimate strength of 120 and a yield strength of 66. We really care about the 120, so we're gonna have an ultimate strength equal to 120 KSI. All right. So let's make a quick guess of the diameter and the fillet radius. I'm going to guess the diameter is going to be somewhere in the range of maybe 2 to 3 inches. Right. So the actual fillet radius is probably going to say, if it was 2 inches, that would be 0.2. And so we'd have That would be way too big right here. So, but it's going to be, that would be pretty large. That D over 10 is a pretty big fillet radius. So let's just pick out the big one, right? So we have 120 KSI, so it's somewhere in between here. So I'm going to say that we have like a 0.85, maybe. It's just a guess, because right here, here's a fillet radius of 0.16, but they were showing like 2 divided by 10, right? So this would be 0.2. So it's up here. It's a big fillet radius. So I'm going to say that's 0.85. So Q, and this is a guess, is 0.85. So now I can get my fatigue stress concentration. So that's going to be 1 plus Q times KT minus 1. So it's going to be 1 plus 0.85 times 1.65 minus 1. I think I put too many parentheses in there. Whoops. So just go 0.65 times 0.85 and add 1. All right. So 1.55. 3. That's my estimate. So that's what my first thing I had to do is I had to do this. Now the next we need the endurance strength. So we know that we need to have all these Marin stress factors, but some of them we could just neglect. We just treat as one. All right, so we can get the Ka. So let's look back at those Marin factors and see where we get all of them. So we have the surface factor. We can get that. We can call it machined, I believe. Let me see. Did we specify anything? Did we say anything for sure? We see rotate. Specify. Surfaces are machined. Yes, they did say. They said surfaces are machined, so we can get that Ka. We don't know the size factor. That's a problem for us, right? So we could guess though. We could kind of make a guess, or we could treat it as 1. That's another thing. That's always an option for us that we could treat as 1, or we could find something in the range that we think it's going to be. The next factor here, we could have the load factor, but this is in bending, so it's going to be equal to 1. The next is the temperature correction. Let's just assume that it's 1, and reliability factor 1. Okay, so really the only thing we have to worry about of we don't know is KB. We could take an educated guess onto that. For the surface factors, right, so let me write down here, Ka is going to be A times the ultimate strength raised to the B. And this is different in the two different additions, or the different additions that we're using. For machined, we end up having 2, A is equal to 2, and B is equal to negative 2.217. So it's going to be 2 times 120 and raised to the negative 0.217. The thing you want to remember is that you don't want to use these. If you get a weird number, you did something wrong. Don't just accept the number, because you might have you're using it wrong, or you made a math error, and this ends up being, so like if you see something that's like way less than 1, you probably did something wrong, right? So that's actually a pretty significant number right there, because you expect something to be in the 0.8 or 0.9 range. And then like for the diameter of the thing, I'm going to pick, assume 2 inches, KB. And we'll take the equation here. That's right there at 2 inches. So we kind of picked a weird one, but it was kind of the weird transition. You could use either one of these. They should come up with the same answer because they show 2 as the answer. So I'm going to go with the 0.91 d raised to the negative 1.57. So that's going to be 0.91 times 2 raised to the negative 0.1157. Should be decimal place in there. So 2.157, make it negative and raise it, and then 0.91. And you get 0.8162. All right. And so we can, the rest of these are going to be 1. We're going to treat it. So 0.7077, 0.8162. We go 1, 1, 1. And then this one is going to be 0.5 times the ultimate strength of 120. Right? I'll put parentheses on there to represent. That's what SE is. So I didn't really leave myself a lot of room if I want to use the margins correctly. So I can multiply those 0.5 and then 120. So I get 34.6566. This is KSI. All right, so now what I want to do is I want to find out, that's my SE. I need to work backwards and figure out what my allowable reversible stress is going to be. So I need to use the SN curve, or the equation for the SN curve. And that equation is this one right here, which also sometimes we're going to use this one, which is backwards, right? And remember what that represents is really it's really this portion right here, right? So it's this is the equation that represents the region between here. So we're going to find the number of cycles, and using this A and this B, which are not the same thing as that surface condition factor AB, use that and find what that stress, that applied stress, the reversible stress, needs to be to cause this number of cycles failure at that number of cycles. And already this video is much longer than I intended to do. So in order to do that, I need to first find these coefficients A and B, and they're found from right here. So I'm going to take that A and that B. I first need to find F. They have an equation for it now in the 11th edition for F as a function of ultimate strength. What is that thing? I don't know. I hope not. But we can also find it from right here. So, oh, nice. Look at that. 120 comes to 0.82 right there. So that's figure 623 in the 11th edition. 120 is 0.82. So F is approximately 0.82. Not just approximately, it looks really close. So let's find F times ultimate, right? Yep, ultimate strength. So 0.82 times 120. And you get 98.4. And we're going to put that back into the equations, A and B. There's A and B. So A is equal to FSUT squared divided by SE. So we get 98.4 squared divided by 34.66. Square that, 34.66, boom. So we get 279.4. And now we want B is equal to negative 1/3 log base 10 of FSUT divided by SE. So I'm not going to fit it into there. It's supposed to be 1/3 log of 98.4 divided by 34.66. And so I'm going to swap that around and go 34.66 divided, and do the log base 10 divided by 3 and make it negative. And I get a negative 0.1511. All right, so there you go. There's the A and the B. We need to find the number of cycles. And according to this, it was going to be operating. So the RPM, I don't want to use an N. And the safety factors. Let's go. We'll go omegas even though we're going to do with RPM. And for this problem, what do we say? 950 RPM? Something like that. 950, where'd you go? 950 RPM for 10 hours of life. So 950 RPM. We want to go L is equal to 10 hours. So for that, the number of cycles, the big N, is going to be 950. That's going to be revolutions per minute. So that's really cycles per minute. And we want to go 60 minutes per hour. And then we're going to go for 10 hours. I should write hours right there. You can see that we're going to get those rid of those and rid of those. So we're going to find out the number of cycles. So 950 times 60 times 10. So 570,000 hours. Or cycles. Now, that's important that it's less than 1 million, right? And it's important that it's more than 1,000, because that's low cycle of fatigue, right? So this is the range in which our S-N diagram is correct. So remember that we're going to take and find this reversible stress, A times N raised to the B. So we'll take 279.4 and take 570,000 and raise it to the negative 0.1511. So I still have those in my stack. I can drop them around and I can just hit the raise to type of thing, and then I can multiply by that. Boom. So I have that. I need 37.73 KSI is the stress that we need to get. We need to subject this to that many stresses for that many cycles to get failure. So we go back to, and we can use the equations that I described today. So one thing you should know is that so the actual stress is going to be KF times the nominal stress, right? And the nominal stress that's going to be happening to this, so it's going to be KF times MC over I. But remember, this is circular, so we can replace that C and the I. I'll just go ahead and do it again. D over 2, right? This is going to be pi over 64 D fourthed. So he cancels out and he cancels out. He's going to turn this in here. So we're going to say that the stress that we would have gotten if we knew the diameter it was going to be 32 m over pi d cubed. But now we're going to set that stress equal to what it needs to be right here. So it needs to be that much reversible. So we're going to be able to write a equation and solve for diameter here, and have that the diameter is going to be the cube root of, let's see, did I do this correctly? He's going to come out and then he's going to come back over there. So he's going to have KF32M over pi, and then have the stress. And in this case, it's going to be the reversible stress that we're going to plug the thing into. So let's see if we get something that makes sense. And we have that stress concentration of 1.553. We have, and then we put a 32 in there. We have what our bending moment is. And our bending moment, where did we get? Oh, yeah, we have 20,000 inch-pounds, remember. We're going to use base units, so make sure that everything is in pounds and in inches. Pi, and then we said that we're going to have 37.73 KSI, but now we need PSI, pounds per square inch. So it's 37,730. And if I didn't make a mistake, and there's no saying that I didn't, I should be able to get a diameter that's in the range, within a reasonable range of something between, I don't know, 1 inch and 2 inches and 3 inches, in that range. If you get like a fraction of an inch, you did something wrong. If you get something that's huge, you did something wrong. So just be careful that you do something, you make sure that the thing makes sense. So let's see. I'm going to take 1.553, multiply by 32, boom, multiply it by 20,000, boom. I'm going to divide it by pi, and then I'm going to once again divide it by that, and then I'm going to raise it to the 0.33333, and I get, look at that, I get 2.032 inches. All right. So if my goal, though, is to make the thing fail exactly at that size, I probably would pick exactly that thing. But I think it's probably better to maybe design this so that you could pick a regular number, right? So use something that's published in table A17 that has the preferred sizes. Some of the thing that's going to complicate this then is trying to work out, well, what is the stress concentration factor maybe that's going to be. Now we're kind of lucky, we could use the 2 inches. We were very lucky that we had the 2 inches. I'm going to make another video where I show where I'm going to, that's going to be a continuation of this video because this one became so long. Where I can put this in Excel and I can play around with the numbers and use goal seek to perhaps do the same process, right? And maybe make small changes where I can try to use whole numbers. But anyway, what I would make as a recommendation, because this is so close to 2 inches, is I would use 2 inches, and then for the other design parts of this, would say, well, this one is going to be then 2.8 inches for this diameter, and then this radius right here is going to be 0.2 radius, and this radius right here, it would be whatever that would end up being, right? So it would be 0.4 maybe radius, yes, for that there. It seems like a kind of a big radius. If you did this on SolidWorks, right, if you took that out and you took a look and saw how big that would be, that seems to me like it would be really large, which is also part of the design process, is to like, does that make sense when you go about the thing? Don't just pick numbers because they work out. So anyway, this is the end of this video. Hopefully this will help you do the homework problem that are assigned. That one is in torsion instead, but we want to try to work backwards and do a design problem. So thank you for your patience.